Hey everyone, welcome back to 3 Deviations. So we finished talking about inverse functions and how to integrate those, and now we're going to move towards approximate integration tactics. There's only really one video we need to do on this to introduce two rules and error bounds. So once we do that, we're pretty much all set, and then we can move on to improper integrals. Then we're done with Unit 6. So approximate integration tactics. So you can't really approximate antiderivatives, so that makes things a little bit tricky. So therefore, we kind of need to become a little bit more open to the idea of approximating definite integrals. So we've kind of put definite integrals on the back burner, but those are going to come back now. So we're going to be talking about definite integrals in the context of approximations and also in the context of improper integrals. So let's get started by talking about some approximate integration tactics. Here we go. So the first rule we're going to talk about is the trapezoidal rule. Now I'm going to forego the definition for now, and we are going to look just at what the trapezoidal rule means. We may have done a little bit of this in the first unit on integration where we covered the sigma notation, but now we are going to be looking at this approximation tactic with trapezoids. So let's say we have a function. Let's say that's our function. And I have a here and b here. So we're integrating this and that. Now what we do for the trapezoidal rule, you may have guessed, is we take, instead of doing tons of rectangles, we take discrete amounts of trapezoids to integrate. We have another one going down there, maybe another one down there, one up there, a lot of trapezoids to be drawn. We keep on going until we get to there, and this is discrete number of trapezoids. This is something we can add up through arithmetic. So the trapezoidal rule says that the integral between a and b of f of x dx is equal to the nth trapezoidal sum, which is equal to delta x over 2 times f of x naught plus 2 times f of x sub 1 plus all the way up to 2 times f of x sub n minus 1 plus f of x sub n. So this kind of makes sense. We're doubling up on these terms here, and then we are dividing it by 2, kind of like that 1/2 base times height kind of thing that you learned in high school geometry. Now, as you remember back from our sigma notation days, we defined delta x as b minus a over n, and x sub I as a plus I delta x. Okay, and now we also want to determine an error bound, because we could have areas in here as well. We could have areas in there as well, and this is going to seem kind of arbitrary, but I'm going to forgo the derivation of this because it's quite confusing. But we say that the error bound is if the absolute value of f double prime of x is less than or equal to some value k on our interval, then we define the absolute value of the error of the trapezoidal sum as being less than or equal to k times b minus a cubed over 12n squared. And of course, n is the number of sums that we have, and then k is this value here, and this is usually like the upper value of our integration bound. So let's do an example with the trapezoidal rule. So find the following integral using 5 subsections and find the error. So immediately we can note that n equals 5, and we want to integrate from 1 to 2 the function 1 over x dx, which can easily be done as a natural log integral, but we are going to be doing this with the trapezoidal rule, so we need to set things up. So we're doing a 5th trapezoidal sum. Now this is going to be equal to 1/5, so delta x over 2. So delta x is 2 minus 1 over 5, so 1/5. We divide that by 2, and then we get all of these sums. So we get f of 1 plus 2f of 1.2 plus 2f of 1.4 plus 2f of 1.6 plus 2f of 1.8 plus f of 2. We can plug this in. We already know our function is 1 over x, so we can find that's equal to 0.1 times 1 plus 2 over 1.2 plus 2 over 1.4 plus 2 over 1.6 plus 2 over 1.8 plus 1/2, which is equal, or well, approximately equal, to 0.696. Now we want to find the error. So to find the error, we find f double prime of x. So f double prime of x is going to be 2 over x cubed. And we're going to be using, or 1 over x cubed, but we're going to be using the upper bound here for our error. So we put in a 2 on the top. So we get 2 over x cubed. The absolute value is less than or equal to 2 over 1 cubed. We're setting x equal to our lower bound. So then we get 2, or which is equal to 2. Thus, k is going to be equal to 2. So now what we end up doing is we will plug this into our error bound formula. We get the absolute value of e sub t is less than or equal to 2 times 2 minus 1 cubed over 12 times 5 squared, which is equal to 0.000666667. So that's the error bound in our actual integral in comparison to this here. So that's the highest amount of error that we'd have with this trapezoidal sum. All right, so now let's move on to Simpson's rule. So the trapezoidal rule was a trapezoid, right? We used a trapezoid. Well, Simpson's rule says that we can use a parabola on that little section. So say if I have discrete little sections, but we define them with parabolas. So we've got that. We get a parabola there, get a parabola there, get a parabola there, get a parabola there. Let's say our function goes something like that and hugs it, kind of. And we get little errors, like little haircuts on the function, little errors on our Simpson's rule sum, but they're pretty negligible. So we define the integral between a and b of f of x dx equal to the nth Simpson sum. And we define the Simpson sum to be delta x over 3 times f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2 all the way up to 2 times f of x sub n minus 2 plus 4 times f of x f of x sub n minus 1 plus f of x sub n. So as you can tell here, we kind of alternate between 2 and 4. That's how that works. And then our error bound goes as follows. If the absolute value of the fourth derivative of x is less than or equal to k on a less than x less than b, then the error of the Simpson sum is less than or equal to k times b minus a cubed over 180 n to the fourth. All right, so let's estimate the following integral with n equals 10, and we'll find the error as well. So we are integrating from 0 to 1 e to the x squared dx, which is an integral that can't be done with our techniques that we've learned. Okay, so we're going to take the 10th sum. We get delta x over 3 times f of 0 plus 4f of 0.1 plus 2f of 0.2 all the way up to 4f of 0.9 plus f of 1. So now we plug this into our function. We get something pretty ugly. We get 0.1 over 3 times e sub 0 plus 4e to the 0.1 plus 2e to the 0.04 plus 4e to the 0.09 plus 2e to the 0.16 plus 4e to the 0.25 plus 2e to the 0.36 plus 4e to the 0.49 plus 2e to the 0.64 plus 4e to the 0.81 plus e to the 1, which is equal to 1.4627. So now we're going to find the error. So the fourth derivative of x is equal to 16x to the fourth plus 48x squared plus 12 times e to the x squared. So now we are going to set this being between that and that. So our low value and our high value of the function. And thus, or the high value of our derivative. Thus we're setting k equal to 76e. So now that we've done that, we can plug in. So we get S sub 10 is equal to 76e over 180 times 10 to the fourth, which is equal to 0.000115. So now what we do is to find the actual value of the integral, we subtract the value that we got from our sum minus the error, so we can approximate this a little bit better. So we get the integral between 0 and 1 of e to the x squared dx is equal to 1.4627 minus 0.000115, which is 1.462. So that's our solution for this last one. Now, this is a fairly it's a weird topic, because this is stuff now we can use our computer algebra systems for. I don't really like these estimations. They seem they don't seem very useful, because we can do so much with the techniques that we've learned, and this estimation can really be done a lot more accurately with the use of computers that can solve integrals like that. So that's my shtick on that sort of stuff. So in the next video, we're moving on to the improper integrals, which is when we do with an integral, say we have a function like 1 over x, right? But I would want us to integrate like this value. Find the value all the way up to there and then back to there. Like when we're dealing with an asymptote. When we need to deal with some continuity